All right. So, welcome everybody for this lovely Wednesday morning, where we are pleased to propose a new version of one of the most exciting part of this practicum, the phase. So, as you know, we had to improvise a new way of performing this practicum in this webinar format, and it's also a chance for us to try to investigate a new testing method, namely the DIC one, the digital image correlation. So we will try to even up a bit and emulate these events. So just a brief recap. So this practicum for you is to perform as a composite repair engineer. So you design a laminate, you induce a load to it with a specific force, and you are able to create your own structural repair manual and validating the expected result through a test, which is a tensile test. So as I said, this year we will use a new technique, which is relatively young, and thanks to our researcher, Richard Samuel, who is nearly graduating, and he was working 6 months on this process. He will guide us through the whole DIC test engine. So basically this whole webinar structure, like a small introduction, what I just did, we will get through the DIC test engine structure. Also Bob, who is also just have been receiving his master, will also be helping us in the setup, and we will try to make it as interactive as possible for you guys. So I would like to highlight the fact that through the fact that we could not physically perform a practicum for us, we are really sorry for that. There was also a lot of frustration from both sides. We tried, Christiana and me, to do the best as we could, using your design, and try to perform as clear and neat repair as possible. But of course, the idea is for you. Can you say again?
Your mic is turned off.
Really?
All this time?
All this time?
But you can hear in the YouTube stream.
Okay, so you could hear me through the stream, I guess.
Only use the Teams for questions.
Okay.
Last week with the you saying that you and another person tried to work on it.
Okay, but I mean, you could, when I started at the beginning, you could hear me or not?
Yes, no, you dropped out. Just close
Okay. Sorry, good. Well, I could again do it, but it's no problem. But what I was saying, well, please take this moment to try to interact with us, which is also a work in progress and process. So don't be hesitant to put questions, ask, if there are things which are unclear to this practicum. As I said, this technology is quite new, so we are really exciting to try to see how we can correlate this to the existing tensile test method. So that's what I wanted to highlight. So I will give in a few seconds the floor to Richard, who will guide us, as I said, to the whole DIC engine process. And by this word, I welcome to us Richard.
Right. Good morning, everyone. As DJ said, I've been working on the system with the Composites lab to complete it. And today we want to apply that to your test samples. Digital image correlation is a contactless type of extensometer. So I think a lot of you are, you know that a contact type extensometer is like a strain gauge, which there's a coil inside, and you have to attach it to the sample. And when the sample elongates, the resistance in the wires changes, and that you can measure the elongation. Or a contact type extensometer, like a clip-on extensometer, where there's two knife edges, and the one knife edge is locked, and the other one can move with the sample as it elongates, also outputting the elongation. The issue with the contact type extensometer is you have to manually put it on the sample by hand, and it's hard to align it exactly with in a vertical or a horizontal orientation. Especially, it costs 10 euros for a strain gauge, per strain gauge, and they're not reusable. So if you're testing a sample for the Poisson's ratio, then you need to put 2 strain gauges on one sample, and that's around 20 euros per sample. And if you're testing for consistency, 10 samples costs a lot of money, 200 euros already. So this DIC system is a good way to analyze the surface components of your test sample once you've loaded it into the bench. On my computer, I have an example of this. Is it loaded? You can see it? All right. Over here is a simple plate with a hole in it. And what happens over here is a camera detects the speckle pattern that is on the sample. This is manually applied by the lab as well. And
I don't see it on the screen.
oh, we don't see it on the screen, Ruben.
Yeah, you see it.
Oh, they see
You
it.
see it?
They see it.
It's
Okay.
delayed.
All right. All right. A virtual extensometer, like the clip-on extensometer, can be put on the sample, which is what you see, this line over here. And the output of that is in this graph. And if I move the slider through the images, you can actually see, based on the elongation of the sample, the stress concentrations around the hole as we sort of move on here until the break. And you can see this through the sort of color gradients. On the right of the screen over here is a legend of the extension of the sample. So how a DIC system does this, digital image correlation, you're going to hear DIC a lot throughout this whole test, which is just digital image correlation, is that if you can imagine a black speckle on a white background, if you were to zoom in with a camera on the edge of that speckle, pixels are going to go from completely black to gray to white. And the gradients of gray between the black and white is called the gray scale. And what the software tries to do is, as the frames, as it tries to correlate the frames, it linear interpolates where the edge of that speckle is based on the gradients of that gray scale.
Can I just interrupt you? I just see a note from a guy who said that he asked if we can make the video, I guess your screen, bigger. I don't know if it's Guy.
Oh, the computer screen.
Yes, Guy, can you turn on your mic and highlight exactly what you mean?
Oh, it's just that I can only vaguely see in the background what's happening. So if possible, could it be moved to like sharing the screen directly on Teams?
The background.
Because then I can see the video a lot better. Because now I can vaguely see things moving in the background. And that's
You mean the main screen behind me?
Oh, I think it's.
But I can't see enough of what's happening in detail to
but
get much from it.
actually, this screen was not meant for you guys to see anything particular. It was more for us to have
Just a brief demonstration on.
Because actually, what is running on my screen, the big screen, is what you should see on the live. So
in the YouTube feed.
Yeah.
So instead of watching Teams, you should watch YouTube.
yes, it's
My
maybe.
apologies. I understand
No.
exactly how
No.
this is working.
Don't bother. It's maybe I should also have mentioned that it's probably better to follow it through the YouTube channel and then having a team as a background.
Yeah.
Is it clear?
So all visual aids should be through YouTube, and then the questions, we're going to be using MS Teams just for questions.
Yeah, correct.
YouTube doesn't allow
Yeah.
volume down slightly. And there's also a bass boost. Maybe we switched it up.
All right. So, so what we want to do today, the general structure of today is I'm going to go pass you through to Bob now. He's going to run a test. He's going to pull a sample with the DIC test setup, and then I'm going to walk you through how the DIC software works, and then we can talk about some of the breaks. So I'll pass you through to Bob now.
Is a bit awkward, so you'll see my back a lot. But currently we have already applied this sample in the test bench.
Can I just?
Yeah,
Little
sure.
check with all of you guys. Is everyone following the session through YouTube? Then you can have the full image. So once again, don't follow it via Team, but have Team only on the background for reactions. Can I get an answer, or can someone turn his mic on and tell me if it's correct, if everything is clear?
I'm doing that now. I think I'm me asking these questions that we don't even go through their work already.
Okay. Okay, so I think Bob can
Okay.
go.
So we did actually most of the clamping already, since it's quite a tedious job to put the sample in. It's quite heavy and we need to apply 30 bolts by hand. And you should have also looked into why we use this particular setup. So why don't we just clamp the steel plates by itself in the test clamp? Maybe someone is able to answer that question. Looking.
Go ahead, because there's a delay.
Well, I'm still waiting on my answer to the question.
Alright.
I think there's a delay in when you ask the question.
Okay.
They can actually hear it.
Okay, so due to delay, I'll answer this question myself. Since the clamps actually only have a diameter of about 70 millimeters, and we're clamping a 200 millimeter wide sample, you get a very large stress concentration around the area of clamping. So what we've done is we use these steel clamps, which are bolted through an aluminium plate, which are attached using glue on the composite plate. And the goal of this is, because if you have a very high stiffness difference in between the clamping, you'll again create a large drop-off in force or high stress concentrations around the area where you're clamping. So we want to have a smooth transition from something very stiff, the steel, again into something relatively stiff in the carbon fiber part. And then the rest of the setup is based on the DIC camera system, which Richard already explained, which tracks the displacement of a sample. In this case, it does that with about 3 frames per second. And we use a blue light to further increase the contrast between the white background and the black speckles. And if Ruben wants to switch to the 3-view system, because then they can actually see the sample. Yeah. Yes. I can zoom in on the sample. And this is actually zoomed in at about at 10 times. And in this resolution you can sort of see how much pixels there are per speckle. And a general guideline is that we should have about 3 to 5 pixels per speckle, at least. And most of the speckles meet this requirement. And if we zoom out again. So the sample is clamped with a relatively high force, because depending on what sort of layup you choose and how well the repair has been designed and has been done, we'll get a result somewhere between 70 kilonewtons and 150 kilonewtons. But you have to imagine that the test bench has to clamp this sample with some sort of a pinch grip, and in that way being able to resist pulling it out with, well, 140 kilonewtons or 14,000 kilos, about the weight of 7 cars. We also advise you to put your volume up a bit, because the bang is quite loud once it actually goes. If there's no questions at all, I can sort of continue with the rest of the test procedure. And I'll ask a question again, maybe this time I'll get an answer. So some of the groups, they choose their layups with the 0 plies on the outside. So the outer layers where the fibers were in the direction of the loading. And I'm quite curious where the design choice came from.
So put their answers in the YouTube comment section.
heard the question of Bob. You can put your reaction or question via the chat format of YouTube. So, looking at my screen now, I can take a look.
I'll answer the question myself again.
Wait.
There's a 30, if you ask the questions, they see it in 30 seconds.
30 seconds.
And then they can start answering. Yeah.
Okay, and how can we get rid of that?
So what you can do right now is just explain what you see in the test benches.
And meanwhile, it might be good to note that we have coupon number 7 in the test bench. I think that should be the sample of Tom and Moki. And based on their calculations, the predicted load is to fill around 108 kilonewtons. But I am sort of ready to start the test.
React. If you want to react through Team, only do it using the video. If you want to type a text, do it on YouTube, because then we have to double check every time message on the Team, and it makes just not easy. So I prefer that if you want to react lively, let's say, use the Team, then we can see your face and hear your voice. But if you want to type a comment and ask a question, do it on the YouTube channel, and you can see that with the whole team. Thanks.
Still no answers to my questions? Okay. I'll keep continuing.
Most of us just did a random layout, is what Christiana says.
Ah. So I'll go into that. There's especially in this test, but even in general, can you imagine why there's it's a disadvantage to have the 0 layers on the outside? And now I have to wait 30 seconds again. I got all the time in the world.
Well, why don't we continue with it, and then when the software is going, we can open up a line of questioning through Teams, and then that will be sort of instant.
That's good.
So execute the test now?
So I'll start the test.
So apparently I get feedback. I get feedback from the guy that's apparently disturbing to have both and the Team and YouTube running simultaneously. So
Okay.
so maybe the as a guy is playing a close team, you just follow us on YouTube.
Yeah, and then that's fine.
If it's too confusing.
Yeah.
Okay.
Once again, it's a work in progress.
So let's just say YouTube, and then any communication can be done through the chat.
Yeah.
We can type that.
Yeah.
Or just speak about it.
Alright, start the test.
Okay, so we're going to start the test now.
Okay. Since we're using a DIC setup, I cannot put the safety screen in front, so we'll have to step back a bit and wear our safety glasses.
Give a voice.
I also predicted go brain. Okay, so that's
Sounds like a bit of delamination.
yeah. Can we actually see?
How many kilonewtons are we at now?
So we're at about 70 kilonewtons.
prediction was that? 105?
109.
100. Alright. Did I get it? Is the price what predicts correctly?
Nope. It's still going, actually. This is a tricky one.
So where did it break?
It broke in the clamp.
Oh,
Because
wow.
you can see the bottom side, it got detached from the alley. Yeah.
Okay.
So field test.
Yeah, so
Maybe you can explain.
so as you can probably see as well, is that we see at the bottom edge of a sample that you actually pulled out the sample out of the alu plate, which indicates that the sample filled somewhere within the clamping, which of course it shouldn't. So what we want to see, and of course have seen with all the, this is test number 7, the previous 6 tests actually broke neatly in the middle, but you always see that during the demonstration it doesn't. But for now it's quite hard to predict what happens, and that's actually why we can deploy the DIC system and then more accurate see if it's unsymmetrical loading or something else. It's hard to see by just looking at the sample happened during the test. I think that's what Richard's going to show you. So he's going to take you through the steps of the DIC and then help visualize the strain field to give an indication of where it filled first.
All right. Did you stop the DIC? The images? Oh no.
Okay. So maybe have a quick look at the images. I'll switch to this one. 7.
It's really hard to find the.
And we didn't stop the DIC system, so we will have to manually remove some images.
I think it's already. Yeah. Probably after, maybe delete everything after 600.
Yeah, it goes here.
There's a question from Daniel.
Okay.
How
Can-
did it spike down and plateau? So why was there a spike down and then it stayed relatively flat?
Okay. So I think we can also answer this question once we have the DIC results. But what is expected is that it's still hold on by the glue between the alu plate and then sheared out. But
So that's why it stayed flat.
that's why it stayed nearly flat. And then every time you see part of it breaking again, and then a different section of the composite plate taking over, and then that couldn't hold the force anymore, and it broke, and just that's the continuous steps of it.
Are these all the images? All the.
Yeah, these are all the images.
All right.
So-
And we get a full screen of. All right.
The software, the DIC software, is called GOM Correlate, and every laminate will have a report that has already the analysis that I'm going to run today. Very simply, a new project is created. If I Control A on all the images, it's just a simple click and drag. We're doing a deformation set of images. And what GOM Correlate does is, based on the names of the images, loads the images correctly in order, like categorically, you could say. So we're just got to wait for a second. I think it's loading at around 600 images, so They are all at 5, I think it's megapixels. Megabytes, sorry. Wait, what's the resolution of the camera?
Also 5 megapixels.
5 megapixels, yeah. So I might take a little bit. It's also strange that this is the first test out of all the tests that didn't fail how we expected it to fail. All right, here we are. So now that the image is in, the software tracks the pixel, the speckles based on pixels. So we have to define how large a pixel actually is relative to the sample. So in the top left here, there is a place, this button over here can define the scale. And essentially, we know the width of the specimen. So I'm going to just control click on both sides. And we are measuring in the X direction. So we want the Y direction to be exactly the same, because then we can say that it's horizontal. So I'll just put this at 50, and this at 950 as well. And we know that the sample is 200 millimeters in length. So click OK. So now it's defining the scale of the image. After that, I'm going to create a surface component, and that is through this this tool up here. And essentially, this is going to create a region of interest on the sample of where what we want to calculate. So normally, I'm not going to speak about it now, but this is based on your speckle size, this facet size and the point distance. This is how much it wants to correlate between each image. So you can see a visual representation of that with these blue squares. So this is 25 pixels across, 25 pixels in length up. But to create the region of interest, I will go down to this button over here, and this allows me to simply just create a region of interest, which I'm going to include the aluminium clamps as well, so that we can see what happened. I'm going to do like that. And this part generally takes about 10 minutes to process all of the images. So during this time, whilst we're waiting for this to be processed, if anyone has any questions, please ask them in YouTube, and we can sort of talk about it. Let's see.
Unmute myself. But so then we switch to Teams,
Yeah.
right?
No,
Everything is going to YouTube.
everything's going through YouTube, yeah.
So Bob, if you stand here before the microphone.
But then I still have a 30-second delay.
Yeah, so they're going to ask a question, and then you'll have time to answer it.
Okay.
So maybe talk about it.
Okay, so I discussed earlier about the 0 ply degrees, and what you can see actually, and this is for example group 5, which as you probably can see, so my sound index, is that this is actually a nice failure around the sample. However, because you remove such a large section of the load-bearing material, which is the 0 degrees, and you have still that ply remaining on the background, and you get some sort of an unsymmetrical laminate, and this results in bending during the testing, and then a peel off of the repair patch. And as soon as the repair patch lets go, it's only held by those edges of the sample, and therefore it breaks at a relatively low force. And you can also imagine that if you have this on your aircraft or on any structural part, which might be prone to being damaged by someone dropping something on it, if your zero layer is the outer layer, this is the first the layer or the layer which gets damaged the most, which might result in catastrophic failures such as these. So that is generally why it's good to put your zero layer not directly on the outside. You have to be careful with the splinters here.
There are a couple of questions. How accurate is this method compared to a normal string gauge?
Richard or me or?
You.
Okay, so this method we've tested it on just general coupons where we applied both the extensometer and the digital system. And although there is some filtering happening on the extensometer, the actual resolution is nearly the same. So we get resolutions of about 0.6 micrometers, which is very small. And generally, I feel like we can replace our current extensometer with the DIC system, especially since it gives much more information than just the extensometer. The extensometer measures only in one direction, whilst the DIC system does a full strength field. So we can also immediately determine the Poisson ratio, for example.
Okay, Guy wants to have a closer look at the sample.
Of group 7, I imagine, right?
I think all samples.
All samples.
No.
Oh, we're gonna go through.
Yeah, we have a special camera set up for that. And then I can move them over there.
Can you put something
Or is there another question which we don't have to walk over first? Or?
Yeah, so he was asking about how did it, so it spiked twice, was that
Yes.
delamination, question mark?
So what we're seeing at the sample now, and I think DJ just took it out,
Oh yeah, you can see that.
is that we can much clearly see damage on the back side, sadly, than on the front side.
Right, we transition to that.
Maybe that would be nice.
DJ, can you explain what we see?
So I think it looks like the damage occurred at the clamping area. And
Yeah, we get some separation between the alloy parts, which should introduce the load into a sample, and you have quite a large region of glue area. And if that region fails, then you can imagine that the area taking out the force, and of course where it's gonna break is where there's the least amount of material, which is in this row of bolts. So if this glue fails in this region, it's very likely that it will break in between the bolts. And I can imagine that we see that actually at the opposite side, if we can take that off.
right, still well,
I get a dry bar.
yeah, maybe.
This region at the back does look like a bit of delamination over here, based on that first failure.
So you want to remove this tab? I think it's still well glued. This side comes out.
Now
Yeah.
you can see.
Yep. Sorry.
Okay.
So indeed we see a well, I think Bob can explain it even better than me.
So again, as you can predict, if this glue fails, then the force will be held onto the area
You have to go more there.
with the bolts. I'll take this off now again. Wearing a mask is not too handy. it's probably in that tensile failure. So it's this area. It's you can all imagine that it breaks at the area where there's the least amount of material. Plus the fact that there's holes which are also bad for composites. Now the big thing is, why did it come off? And that's a much harder question to answer, I'd say.
But we do have a crack there, and also one on this side.
Would be interesting to see how it shows up in this area over here with the DIC, because obviously we can't see anything when we're just looking at it whilst it fails. So.
But what we see is that the repair stayed intact. So the question is, was it too stiff regarding the original laminate, or did it do the expected job?
And this might also be sort of. Just don't think. So
No,
the
no,
first failure, we heard about 45 kilonewtons. I think we'll also see that in the graph and on the DIC system, and it might very well have been where the alu plate already separated from our composites. But again, it's very hard to predict, and that's why we have DIC.
Yeah. So using DIC, we were able to track down.
Yes, more likely.
Yeah.
Alright, so we have a question from G. What about certification for the aerospace industry? How do you think, guys, this will be possible and in what time frame?
So there's a specific ISO standard.
Yeah, good. 9513. Good.
There's a specific ISO standard, so 9513, which is related to tensile testing, and then specifically to measurement systems for the measurement of this elongation or strain. And procedures are described in the standard for an extensometer, how to calibrate it, for strain gauges, what sort of requirements they should meet, and also for an optical device such as a DIC system. So a certified institute could also certify this DIC method to comply with the ISO 9513 standard. So yeah, it should be possible even for the aerospace industry.
Someone is asking, damage due to drilling possible?
Yes, yeah. So in this case it is, but if the alu plate transfers the load to the composite plate through the glue layer as it shouldn't break at the area where it did. So it could be due to some bending, due to the clamping, and this is also something which is very typical for testing, is that it's relatively quite difficult to test something properly, and so we already need to design this special fixture, but even in the fixture there's some room for error because it might not be perfectly aligned, or some other phenomena might happen which results in a non-equal distribution of the force or some bending in the plate, and then 1 out of 7 might fail like this.
Alright, can you repeat the question by the way? Also the damage could have been introduced during that drilling, no? Daniel's asking, so not a full row failure. So it's not through the entire row. Can you repeat the question?
So I don't think it's a good observation, is that indeed we don't see a full row failure. So it filled in the, I think about 4 holes is where it filled, and then it's still cracked in the area in between, and this is also, again, it's very difficult to predict what happened, because you can also imagine there's some sort of a dynamic effect. So once a certain region of the laminate fills, there's a
Need to scroll down a little bit, I think.
dynamic reaction, and that could cause failures in different regions. So it makes it quite difficult to predict what happened. And this is again where the DIC might reveal some answers.
I also see a question from Guy saying there could have been some dust in the glue in the part static failure. So I can also answer to this question where we took care as much as possible to prepare the plate for having a perfect bonding. So everything was removed and prepared for having to remove all the any kind of element which might be contaminating your plate. So I don't think that it might be a possibility, but I don't think dust was an option. I also see, so I hope I answer your question, Guy. I also see a question from Mariska, who is asking, can this method detect bending? If not, will this be looked into in the future?
So, do I still need to repeat the question? Or?
No.
Okay. So, it depends on how you look at bending. So, if you look at bending from a side view, it would be possible. However, the current technique, which is a 2D DIC system, does not allow for visualizing depth. So if you look at bending from the top side, for example, a 2D DIC system doesn't work that way. And you need to have a stereo setup with 2 cameras tracking to allow you for a 3D vision, basically. And that's something we still need to look into. Good question, by the way.
Yeah.
How far is the processing?
It's about 80% there, so
Okay.
it is one of the disadvantages of the DICs that the test can take a little longer than what a common extensometer can give. So,
and I think that's also something which we originally thought we need to have a camera with as much megapixels as possible, because then you get sort of smaller or more pixels over the same area. But the issue with that is that there's a trade-off between the amount of time it takes for the actual processing to be done, and this is also why we capture photos at a relatively low frame rate. And separately, there's also a limit to how small you can make your pixels.
Yeah, indeed, I see a funny reaction of Chris saying that it would have been indeed a lot of dust if it was debonding there. So
But,
as I said, I'm quite sure that we tried to do a neat job to make sure that everything was.
your mic is off.
Is it off?
Oh, yeah, I think it's from out of battery maybe.
Yeah.
Really?
Yeah. Okay, both go.
Okay.
There's no more questions.
Okay.
I think we switch to Richard, and then we'll have a countdown.
Yeah.
Yeah, yeah, right. So this computer. I can
No,
also
don't
talk
Because
about
how many times does it take to need to load?
This one.
Alright, so I mean
We've taken 634 frames and it's processing them a little bit slowly, but we are at about 548 frames, so that's fine. Essentially, what we want to do is attach an extensometer, a virtual extensometer on the left, on the outside of this repair, and that's going to allow us to actually see how much it elongates. But more so, the more interesting side is we're going to apply a strain field over the surface component that's taking a while to process, because then we can actually see how it behaved in the clamps, the actual sample behaved in the clamps. So yeah, we're almost there.
And maybe you can answer this question.
Yeah.
So they say the sample looked gray instead of black.
Yeah.
Maybe repeat it.
Oh, the sample looks gray instead of black?
Yeah, and this is due to the fact that the separation was between the glue and the alu. So the glue is still on the carbon fiber,
Yeah.
So what you see with the gray is, and you have to repeat all this because they can't hear me.
Oh, okay, okay.
And what you see is actually the glue. So
What-
and the glue is gray.
Oh, I see. Okay, okay. So if nobody heard Bob, the question was why is the laminate gray, and that is basically because of the glue that was in between the sample and the alu clamp or alu profile. Or what would you? Yeah. So that's it's just a coating on the outside, but yeah, it doesn't seem like there was any failure in the middle of the sample except for on the top left there, where we saw a bit of delamination, but we'll see what the DIC says. We're almost there. We only got about 13 frames to go.
You quickly switch here, I can show you, and then the other plates.
Yeah, yeah.
I'll just
Bob, but about what we're talking about now.
Can I share a question in between? So I
Yeah.
have a few questions popping up. I have one of Daniel. Isn't it better to use the color maps over grayscale? That way depth can be perceived.
Say again, is it better to use?
To use color maps over grayscale. That
So
way
maybe
depth
it's-
can be perceived.
Oh, so to address Daniel's question, I don't know if you heard DJ. Isn't it better to use color maps over grayscale? That way depth can be perceived. Well, a 2D system isn't really, it's not used for depth, for any sort of that calculation in depth. It's just for a 2D plane. And colors can create more saturation in that grayscale, or the difference of the white edge and the black edge of a speckle. So actually the camera is used that we use is a monochromatic camera, which is black and white, and that is, it's purely just to highlight the contrast between black and white, because then the images are actually exported in a .bmp format, and that is sort of a bit format that tracks. It's only based on the gradient of the pixel itself. But anyways, I think this is ready. Is this ready? All right. Okay, so now that we have the surface components, there's a tool over here that can add anything that you sort of want to calculate for it. So the strain, which is the epsilon in the x direction or the y direction, and the displacement or minus strain. There's a lot of functions that you can apply, but for now we want to go for the strain in the y direction. And this creates that sort of function over the field that we created, the region of interest. Oh, I didn't. That's actually a good idea, but that's more for the extensometer. More calculations. Takes a little bit of time. It does take time now as well to do these tests on Bob's computer, because we're running the OS. Is it OSI? OBS. We're running the stream off the computer as well. So before I continue as well, I am going to set an alignment with regard to the region of interest that we set. This is to ensure that, you know, whatever it is calculating is in the right direction. So to do this, I'm setting the z-axis on the edges of the region of interest. Sorry, this is just to set the orientation of the axis. So do this, and you can see that the Y direction is pointing down, we can change that with this button here. So once that's done, we can actually then set a virtual extensometer to see what happens in these directions. It's taking a little bit of time. Okay, I've sort of, there we go. Yeah. Don't know, it's just, I think it's applying this to, there we go. No? Oh, saving. Yeah, so it does save the file every 10 minutes so that you don't lose your work, which also takes time because it's got to save all 600 images or whatever you've applied to those 600 images. So you can imagine for faster test time, you need a pretty strong computer. We're running it off a laptop, which is actually i7. Yeah, I've got an i7 laptop, Bob.
I can answer one more question from Mark. Yeah.
You can see the question.
So quickly in between while the workspace is saving, I see a question from Marco. Can this DIC method also be used for compressive testing? So you could visualize the strain on during a compressive test. However, a requirement from the ISO or ASTM standard for compressive testing is that you visualize the strain on both sides of your sample to make sure that there's no bending and that it's purely compressive. So typically you have to apply a strain gauge on both sides. So in this case you would have to apply, to completely comply with the test, you need to have a camera on both sides of the sample. I think, yeah, and indeed, good excuse for a beast PC.
Still saving. Any more questions?
I don't know.
Oh, am I in? Sorry. Sorry, I was just checking out the
Let's switch
questions.
back to, I think,
Oh, no.
should be ours, don't say.
Is it saving?
Yeah, it's also, it comes in the streaming
Okay, so
full HD over 5K.
now we're back. So the alignment's been set already based on the strain field. If I drag the bar, you can see this is already elongating a lot faster than everything else. So we're pulling the sample out of the actual grip. And the more I continue, you can see it actually at the top here. So it wasn't actually only the bottom side, but the top side is coming out. Yeah, there it is. So the top side, it looks like there was actually a failure at the top side, which was that first dip that you saw in the graph. So, okay, I'm going to create a extensometer so that we can actually see what happened. Say again?
I should one and it needs to calculate some steps, but this should be relatively.
Yeah, that should be quite. I'm not going to put it on the alu though, because there's no speckles to track there. So I'm going to select in the Y direction. And yeah, this is good. There we go. And we're going to choose for the change in length in the Y direction over here. So here we see the graph. And if I click and drag over here, this is the first crack, the first sound that we heard, that dip. And it looks like it failed actually towards the top area. Is that true on the sample? And yeah, as we go along, this graph just shows us the strain field, so the strain percent, sorry. And we can see the break at the bottom over here.
Yeah, actually, if you go back slightly, right, you can see the first field on the left side.
Yeah, yeah.
So now the right side is taking up more force. And you have to repeat this because they can't hear.
Okay, so it first fails. You can see on the right side over here, or the left side, you could say, and because of that, it breaks through the whole sample. You know, there's a small buildup of stress over here. You can see it in the actual laminate itself. But yeah, lastly, all of your samples will have this analysis on it, and we can run it through a report format where the file can be exported as you know, a small video with the diagram itself on the right side. So if I fix this real quick, I can enlarge the image. And you know, these things take a while to process, but once it's done, you can clearly see and make a prediction on exactly what happened to your sample.
And maybe it's good to note as well that the change before the break is now quite low because we have such a high percentage after break. Which so we could optimize the results by skipping all the results before the break, and that would
Yeah. Skipping the results before the break.
so everything after the break.
Okay.
It's a full skip.
Oh, all right. Well, I mean, no, yeah, I mean, right now all the software is doing is exporting it into the reports, a report format. That also takes a little bit of time. But if anybody has more questions, we can also discuss that. Let's have a look. How effective, Guy asked, how effective would this method be for 3D shapes? Bob? Yeah, I mean, I can answer. A lot of the testing that I did with this setup is purely 2D. There is a lot of research that is done on 3D test setups. I can't vouch for how accurate it is, but it is an upcoming technology. So it's a very young technology that's got active testing. The only thing is, every DIC test setup is specific to what you're testing for. So if you would want to do a 3D analysis of these tests, then research would be put into building a 3D DIC sort of test setup specifically for the bench at In Holland Composite. So it is also another disadvantage of a DIC system, which is very specific to the test parameters that you're actually testing for. But do we have another one? Another question? No. I think that's pretty much.
There was a question about both sides. I think you already traded.
Bob
Yes,
answered that one,
okay.
yeah. But it is surprising how accurate the system can get to just using pixel tracking, because if you 1 pixel for this camera is 3.45 micrometers, and if we are tracking with strain percentages with a difference between I think it's 0.032%, we are essentially tracking sub-pixels. So it is quite impressive for just using a simple 5 megapixel camera running at 3 frames per second.
So if I may ask, what do you think, what could be your recommendation if we want to proceed?
My recommendation?
Using this technique? And related, for example, to this practicum.
Yeah, I mean, a recommendation for this is to do more tests, maybe on the same sample with different functionalities, and actually see how accurate that is based on a strain gauge or a contact type extensometer. The toolbar that I use to create the extensometer or the surface components or whatever it is, there's a lot more that the system can analyze, whether it's the Poisson's ratio, or if you're actually able to correlate the test bench force with the images itself, you can start to do actual stress analysis across the whole sample. So there's a lot. It's a young technology that can be explored a lot, I would say.
Yeah.
Okay, so and what sort of data are we gonna? So I think we supplied it with a small video of their own sample.
Yeah.
And the report you just created.
Yeah. So the report that I've created over there, I think it should be done now, right? I don't know. Can we? Oh, let me show you for a second. Can we go to the computer, Ruben? Yeah. So this report is the final output of the sample. You can add a title over here, but if I click play, it will show. Yeah, there we go. It shows a video of the sample in correlation with the graph and the legend with the color scheme of exactly what you're seeing. You can pause it or play it or whatever it is. I believe you have to have GOM correlate to run this. It is free, so that's fine. But all groups will have this report format for their specimens. So you can then sort of have a look at it, maybe give a brief description of where you think it failed or why you think it failed based on what you see in this report format.
I saw a little remark of Guy saying, can we have a coffee break? But I think we're
pretty much finished.
Yeah, we are pretty much finished for now. And Guy is also asking if is it like a real life FEM model?
Yeah.
More or less.
Yes.
Yeah.
Pretty much.
More or less, says Bob. So as Richard said, you will receive then, so they receive a PDF format with the, yeah? Yeah, so important remark, when you receive in your PDF format, there is how can I explain, a note which will pops up and says, maybe you can explain better than me, Rich.
Yeah, if I have the, all right. When you get the report, so in the format, don't click the OK button when you want to export it to a PDF file, because you need the professional version to do that, and that's
it's more,
very expensive.
I think it's more about Adobe Flash Player.
Oh, sorry. It's about Adobe. So I thought
no. So when they receive we have to explain it again. When they receive the PDF document, they will open it. There will a reminder of Adobe which will pops up and says, if you want to activate Adobe Flash Player,
Disable for future uses.
yes, if you want to disable Adobe Flash Player for future uses, click OK. Don't do that, because if you will do, you won't be able to see your video playing. So yeah, it's the main thing. But when we will send the file, we will put this again in the mail. So
Which might be helpful.
I think.
And maybe it is interesting, if they do want to have the entire data set and try GOM, because it is free software, we can supply it.
yeah.
But keep in mind that it's about 4 gigabytes.
Yeah, so of course, if you want to experiment yourself with the GOM software, it's an open source, and we can provide you the link or whatever, then you can yourself experiment with it. So, so at the end of all this, you will, based on your conclusion of this test method, you will come you will deliver your report and your analysis, and that will be the end for this practicum.
All right.
So I hope you find this moment insightful. That it could, let's say, even up with the real physical practicum. Please let us know through the chat or even later on through team, what was for you important to follow. There is for sure room for progress. As I said, it was for us the first attempt with trying to make the webinar practicum. So of course, room for improvement is for sure there. So with those few words, I think we can say that we are ready for now. I see nice feedback. Great to see Mariska is saying thanks for your demonstration. It was very interesting and educational. Daniel said he's satisfied with the demo. So yeah, as I said, we try to make it as lively, interactive as possible. Yes. So thanks a lot, guys, and
Thank you.
see you next time. Thanks for the question. Bye-bye.
Sort of makes your finger tired after a while.
Like 5 minutes per plate or something like this?
Yeah, something like that. And I was thinking as well, because the biggest motion is pushing it back and forth, but then pushing it in at the back. So you go like back, down, and up, sort of like that. So I was thinking of actually having it on and just doing this with the motion, and that does work. But then after a while, it just stops really. So it has to be in those bursts, but it just takes quite a while. Whoa. I think you know when it's sort of complete when if you take a step back and it doesn't look white anymore, it looks sort of grey.
quite hard. I remember. Almost there.
Yeah, that's about done.
Good.
Yeah, that's about good.